All right, so let's have a look at the graph of sine right here. Looking at the graph, would that function have an inverse? And how do we know it has an inverse? So there is one very big property of functions that needs to be met in order for a function to be invertible. All right. Well, number one, this graph represents a function because it passes the vertical line test. Right. That's number one. However, a function is invertible for another test. What is that test? Does anybody remember that one? If so, which one is it? Yes.
I think it was, I can't remember the name, but it was one-to-one. So
It's a one-to-one. So yes, the function has to be one-to-one in order to be invertible. That is true. That is, all the y's are only taken on the ones, right? Like for example, a parabola. This value of y is taken twice, so that's not a one-to-one function. And another way to describe these one-to-one functions is whether they pass or fail the horizontal line test. So we have a problem with the sine function, right? Because it fails the horizontal line test. And but still, there are inverse trigonometric functions. So what's the way around then to define these inverse trigonometric functions? Well, so we need to restrict their domain. So we need to take only a small portion of the graph in order that it doesn't pass or that it doesn't fail actually the horizontal line test. So what if we just take this portion, do the horizontal line test? That horizontal line will only cross once, so in this case, we need to make some restrictions, of course. What are those restrictions? So we need to restrict the domain to negative pi over 2 to pi over 2. And the range, well, the range remains the same. That always goes from negative 1 to 1. All right? Right next to, so when we define the inverse trigonometric function for sine, which is denoted either y equals sine the negative 1x or arc sine, either way, those are the two ways to denote the inverse trigonometric function. Well, let me just draw the graph for this, and it's going to look like this, something like this. And well, the properties of this trigonometric function, essentially they get reversed. When we have the domain and the range of a given function, the domain and the range of its inverse, they just get reversed. So the range of the function becomes the domain of the inverse function, and the domain of a function becomes the range of the inverse function, right? Same situation with the cosine function and the tangent function. So again, we have issues with those two functions because again, these two functions are not going to pass the horizontal line test. Therefore, they're not going to be one-to-one and not invertible. But a way around this is to take only a portion of the graph for which the function will be invertible. All right? So let's see. Restrict the domain. In this case, we need to restrict it to 0 to pi, and the range remains from negative 1 to 1. Of course, well, we can define the graph. Let me just give you the graph of the inverse or the arc cos function. Arc cos x. And we'll just interchange these domains and ranges. Negative 1 to 1 and 0 to pi. For the tangent function, okay, this one is going to have a couple of very important properties that we need to take into account for the following section when we evaluate limits at infinity. You'll see. Well, again, the tangent function, horizontal line test, fails because it crosses more than once. So it's not a one-to-one function. What do we need to do in this case? Take only one portion of the graph. Okay. If we restrict the domain from negative pi over 2 to pi over 2, and the range, okay, what would be the range of this function? Is it still negative 1 to 1 like sine and cosine?
Negative infinity to
Negative infinity to positive infinity. And be careful with grouping symbols because for infinities we always use the parentheses, right? So let's see. Let's define its inverse function. So pre-calc you saw the graphs for this. And in particular, we need to also reverse the direction of the vertical asymptote. So for this inverse function, those vertical asymptotes become horizontal asymptotes at the same values as they were in the original functions, right? But in this case, this is y equals negative pi over 2 to y equals pi over 2. So in this case, well, for the domain is all real numbers. So actually, for the grouping symbols for the domain, it's also parentheses. And the range goes from negative pi over 2 to pi over 2. And well, let's take a moment and have a closer look at this function, at this inverse tangent function, because we will need these properties for later. So let's see. Let's have a look at the limit of arctan. This is y equals arctan. As x approaches infinity. So what's the limit as x goes to positive infinity in this case?
pi over 2.
Pi over 2, right? So for large values, the largest value the graph takes in this case is bounded above by pi over 2, all right? Okay, so this is pretty much a basic review of the pre-calculus of the inverse trigonometric functions, more like the properties and their graphs. Any questions about this so far? All right, let's have a look at more algebraic manipulations involving inverse trigonometric functions. Well, one thing to keep in mind here is you need to take into consideration all these definitions of trigonometric functions. Well, I'm talking about SOHCAHTOA, you know, in terms of triangles. So actually, there's a couple of ways to go back and forth between the values of the trigonometric functions and their angles. Some of you may have learned the unit circle. Some of you may have learned the what else? The triangles. I use triangles because they're a lot more closely related with opposites, hypotenuse, and adjacent. But if you want to use the unit circle, did they have you memorizing the unit circle in pre-calculus? That's fine, and provided you feel comfortable with it. Okay. So let's evaluate some of the values right here. So without using a calculator, what's arcsine of negative root of 3 over 2? All right. So again, in this case, you can use the unit circle or you can use the triangles. So, and need to be very, very careful with the domains of these trigonometric functions because these don't work for all real numbers the way the original trigonometric functions do. In this case, recall that we have a restriction for arcsine. Recall that arcsine only works between negative pi over 2 and pi over 2. So if you use triangles to answer this question, you might want to shade the region where this arcsine function is defined. That is, in this case, quadrants 4 and 1. That's when that means negative pi over 2 to pi over 2. All right? Now, in this case, notice we want to find out which angle has a negative root of 3 over 2. So in this case, we need to take into consideration which quadrant has the sine function negative. So the question is sine negative in the first quadrant or in the fourth quadrant? In the fourth quadrant. So I'm going to draw a triangle in here. And I'm going to say sine, which is opposite, negative root over 3, where hypotenuse this is 1, and I believe this should be negative pi over 3, right? Of course, again, if you memorize the unit circle, I believe in some cases it's easier to look at the unit circle and just look at negative root of 3. Where is it? That's the y coordinate in the unit circle. Just look for the angle. Arctangent of 1. So which angle has a tangent of 1? You can use a unit circle, you can use the triangles, either way. Yes.
It's pi over 4.
It's pi over 4. All right. So how do we get that? Well, there's a couple of ways to get this one. Well, you can look at the unit circle, divide the x and the y over x. That's what the tangent function is. But another way to say this is arctan, which is the same as saying 1 over 1. And if we do a right triangle here, that's 1 over 1. And that's actually the 45 degree or pi over 4. All right? So again, well, you can play with these values. A lot of you, we're going to use this when we're evaluating definite integrals. We'll see how they're going to come up. All right, so let's look at the next one. So for letters C and D, what do we have this time? We have compositions of functions. So we have cosine of arc cosine, and then we have arc sine of sine. All right, so one of the most, let me say, most memorable cases in which we use inverse functions, compositions of inverse functions, was when we defined, and we had this case, e to the ln of x, e to the ln of x, and ln of e to the x. What are these two expressions equal to? It's just x, right? So, well, this is a tool that you use, well, number one, to find compositions of functions, or to solve equations that involve exponentials and logarithms. You know, all they do, they cancel, right? And so a very similar situation we have with cosine of arc cosine, arc sine of sine, well, depending on the order of this composition. Well, as opposed to the logarithms and the exponential, we cannot just cancel them. Yes, even though it looks like, well, they're inverses to one another, just cancel them. Unfortunately, in this case, we need to make sure that the restrictions are taken into consideration. But well, so what is arc cosine of 1 in this case? So in this case, can we simply cancel these ones? Well, so number one, what is arc cosine of 1? What angle has a cosine equals to 1? 0. Cosine of 0 is 1, yes. So cosine of 0 and, well, what is cosine of 0? That equals back to 1. So in this case, we are good with it because we are getting values that are within their corresponding domains and ranges. in this case, we can just say cosine cancels the arc cosine. Now let's have a look at letter D, arc sine of sine. So would it be the same situation? Would we be able to just cancel arc sine with sine in this case? No, why not?
Restrictions.
Restriction. So notice that the arc sine function that only takes values between -1 and 1. All right, so we're going to have some issues right here. Number one, let's compute this quantity in, from later to later. So let's do the innermost first. Okay, so what is sine of 7 pi over 6? It would work, of course, to draw Cartesian plane. 7 pi over 6, I believe, it's right here. All right, and I believe this is going to be -1, root of 3, and 2. So sine of 7 pi over 6, isn't that -1? Alright, sine of -1/2 rather. Alright. However, there is an issue with this with this calculation right here. If you wanted to do the arc sine of that to get back to 7 pi over 6, the problem with 7 pi over 6 is that 7 pi over 6 is not in the domain of arc sine. Recall that the domain for arc sine only lies in the first two quadrants. So what do we need to do? We need to move this angle to either the first or the fourth quadrant where the sine function is negative. And again, that's going to take us back to the fourth quadrant. And in this case, well, you might be thinking, oh, that's 11 pi over 6. Yes, if we go counterclockwise with positive angles, but again, 11 pi over 6 is not in the domain of the arcsine function. It's not part of it. So what do we need to do? Well, let's call it a negative pi over 6 in this case. All right. Any questions about it? All right. Let's see. So let's look at other types of problems in which we have other compositions. For example, C and D, well, we were working with values that can be found on the unit circle, like 1/2, 0, 1, root of 3 over 2, root of 2 over 2. Well, we didn't look at all of them, but basically we'll look only at those values. What do we do when we have these quantity expressions right here, like, for example, what angle has an arcsecant of 6/5? I don't know what that is, and in fact, we don't even need to know what the angle is. So the way we're going to go about these ones is by setting right triangle, use the Pythagorean theorem, and get the missing side. So number one, I would rewrite this expression the following way. So let me write this as a tangent of theta, some angle. Because we are going to set up a right triangle for that angle, but again, we don't need to know. It's not necessary to know. But in this case, let's relate this arcsecant to theta. I'm going to do this on the side. I'm going to set arcsecant of 6/5 equals some angle theta. Of course, we can go back and forth between, well, I mean, let's assume that the restrictions are met and all that, and let's say that secant theta equals 6/5. And then from here, that's where we will set up our right triangle. And here is where our SOHCAHTOA is going to come into play. All right, so secant. Using SOHCAHTOA, what's secant?
Sine over cosine?
It's sine over cosine, sine over cosine. I believe that's tangent.
Yes.
All right.
Yeah.
Mhm.
It's one, it's
Yeah.
1 over cosine.
It's 1 over cosine, right? When in terms of hypotenuses and sides, how do we define that? Yes.
Awesome. Hypotenuse over adjacent.
Hypotenuse over adjacent. So that's hypotenuse over adjacent. That is, the number 6 will go here, and the number 5 will go there. So we need that missing side. And let's see. So we're going to use the Pythagorean theorem to find the missing side. So that's c squared equals a squared plus b squared. And c squared is given, so that's a 6 squared equals 5 squared plus b squared. All right? So that's a 36 equals to 25 minus b squared, or rather plus b squared. And b squared equals 36 minus 25. Is that, how much is that? I believe that's 11. And b will be the square root of 11. And I know in this case, because we're using the square root property, technically we have to use the plus or minus, but in this case, that's fine. All right? So now that we know all the three sides, we have all the information to answer the initial question. Tangent of given this value, so in this case tangent, which is opposite over adjacent, that should be square root of 11 over 5. Final answer. Questions about this example? All right, in a very similar way, we are going to have another composition, but this one doesn't have any values. Actually, well, it has one value, but this one already has this variable. So, and this one is very important. This idea, we're going to use it now that we're going to get into the calculus of the inverse trigonometric function. So, in the same way, I'm going to define this cosine as some cosine of some angle theta, where all this expression inside of the parentheses will be related to theta. That is arctan of x over 4 equals to theta, which means that tangent theta equals to x over 4. And we're going to use this information, this mini equation, to construct a right triangle, find the missing side, just the same way we did it before. So let's go ahead and do that. Again, okay, SOHCAHTOA for tangent, what is it?
Opposite over adjacent.
Opposite over adjacent, so that's opposite over adjacent, where the opposite is the x and the adjacent is the 4. So we need to find the length of the hypotenuse, and well, we can just use Pythagorean theorem, c squared equals a squared plus b squared. And c squared equals x squared plus 4 squared, which is x squared plus 16. And c is just the square root of that. So we have all the information that we need to answer the question. We want to know the cosine of this. And well, you might ask yourself, why are we doing these compositions? I mean, yeah, they make sense and all that because we're using the SOHCAHTOA, we're using the Pythagorean theorem and the triangles. But these are going to come up later when it comes to trigonometric substitution. When we evaluate this kind of integrals, we need to have it like really, really sharp. All right, so okay, cosine, which is adjacent over hypotenuse, that's 4 over the square root of x squared plus 16. All right, and that's final answer. So that is the pre-calculus and the algebra of trigonometric functions. Okay, so let's have a look. Question?
How do you go from arctangent to tangent?
From arc, oh, okay, because of the inverse properties.
Okay.
You know, when we have like, when we have, okay, arctangent, what was that? Okay, x over 4 equals theta. So what I did is to do the inverse of arctangent, which is tangent and tangent. And in this case, cancel, and we're left with
Okay.
tangent equals to x over 4.
Mhm.
Right? Okay. Any other questions about the calculus of inverse functions? Well, let's have a look. Let's go ahead and do the calculus, the derivative of inverse trigonometric functions. Well, I mean, taking the derivative of a function, I guess at this point you know how they work. The product rule, the quotient rule, the general power rule, the chain rule, all of those will be applied in this section. What else? Even an implicit differentiation. But let's do the exercise of deriving this. Well, we're going to do only one derivation. We don't have to do all 6, of course. So we're going to find a formula to derive to differentiate the arctan function. All right. So number 1, let's start with the following. So we have the function y equals to arctan x. All right, of course, I mean, we went over this, we went over all of this about finding inverse functions, so that's what we're going to do. We're going to take tangent on both sides to get x equals to tangent of y, all right? And we're going to take the derivative of this function. However, we're going to differentiate this implicitly, because in this case, we don't have a function, an explicit function of y. We have an explicit function of x, but in this case, it is y that depends on x. So that's why, well, in this case, we use implicit differentiation. All right, what's the derivative of x? 1. All right. What's the derivative of tangent y, of tangent? Secant squared. Secant squared y, all right? But when we I am missing something here. What do we do when we differentiate y implicitly?
You got a dy.
We need to multiply by either y prime or dy dx. So I use dy dx. I think it's more explicit about what a derivative is. But of course, if you want to use the prime notation, that's fine. Okay? So let's treat this now like an equation. So what I'm going to do here is to solve for dy dx equals to 1 over secant squared y. But there is a problem here because we want to find a formula in terms of x because it is the y function, the one that depends on x. And that formula right there that I have so far, it's not a function of x. So we need to, well, number 1, let's use identities here to something more useful, I believe, or easier to work with. In this case, I'm going to move this secant squared as cosine squared in the numerator, right? So what about this one? Okay, number 1. Let me write this in parentheses. I know there's really nothing big in here, but it's going to be a lot useful. Okay. So in this case, let's set this cosine y equals to x. And we're going to use the same triangle situation to rewrite that expression in terms of trigonometric functions trigonometric functions and functions of y into functions of x, because again, the derivative that we want has to be in terms of x, and this is not in terms of x yet. Now the real trick here is that this cosine y is not very explicit about how to set up the triangle. So the trick here is every time you have one equation like this, put an over 1 in the denominator. That way it's going to be a lot easier to see that this is the SOHCAHTOA, which in this case is the adjacent over hypotenuse, isn't it? So let's set up a triangle for hypotenuse over, okay? So let's see. So hypotenuse, which is 1 over, oh no, which is x, and the hypotenuse, which is this, which is 1. So let's find the length of the missing side. All right, so from here, well, I don't know why I have an arctangent function in this case. For whatever reason, I got an arctangent. Oh no, yes, it's not from here. It's from the arctan function. Never mind. So let me scratch that part. It is from the arctan function. So from the arctan function, which equals to y, tangent y equals to x, which is an x over 1, which in this case, this is the opposite, and the hypotenuse, and the adjacent rather. So let's construct our triangle from here. Opposite over adjacent, and the length of the missing side is obtained by using Pythagorean theorem. So x squared plus 1 squared, and c equals the square root of x squared plus 1 squared, which is 1, which is going to be that quantity over here in the hypotenuse. All right, and now we have all the information to rewrite this cosine of y in terms of x from the given triangle. All right, so cosine, which is adjacent over hypotenuse, so goodbye functions of x, welcome back functions of, functions of y, welcome back functions of x. So that's going to be 1 over the square root of x squared plus 1, quantity squared. All right, so in this case, if we square the number 1, that's going to be 1. And if we square the radicals cancel. And that's going to leave us with x squared plus 1. Right? Which is indeed the derivative of the arctan function. That's formula number 3 right here. Of course, the formula that I derived over here was to differentiate just arctan of x, right? However, of course, keep in mind that a function can be composite to have a more complex form inside of the parentheses, and this case, right? And in this case, we need to take that into consideration. So the forms that you have for the derivatives right here involve the chain rule, multiplying by the derivative of the function or the expression that is inside of the parentheses, okay? So let's have a look at some examples. Of course, these formulas you need to memorize this, at least memorize the first three forms. Notice the remaining 3 are just the ones with opposite sign. All right. So memorizing the first 3, you can memorize it. You can get the other ones. All right. Let's have a look at some examples. So. Find the derivative of each function and simplify. So most importantly, we need to simplify these derivatives. So let's see. Find the derivative of each functions. And okay, h of t equals to 4 times arctan of 2t. So notice in this case, it's not just arctan of x, so there's a linear function in this case. And well, so we need to identify that derivative for arctan. In fact, that's the one that we just derived. Let me have them here for our reference. Okay, so the derivative of arctan in this case is 1 over 1 plus u squared, where u is the quantity inside of the parentheses, and then multiply by the derivative. So h prime of t, okay, that's going to be that constant multiple 4 times the derivative, which is 1 over 1 plus 2t squared, times the derivative of 2t. And what's the derivative of 2t? 2, all right? So that's 2. Well, all we need is to simplify this one. So we need to multiply 4 times 2, which is 8, and divide by 1 plus, what is 2t squared, by the way?
4t squared.
4t squared. Be careful, because a very common mistake, and I did that a lot as a student, I usually forgot to square the coefficient as well. So in this case, that's because both numbers are inside of the parentheses. But otherwise, if only the t had the power, we don't square that coefficient. All right? So that is derivative, right? Let's look at another example. Differentiate 16 arc sine of x over 4. Quick. We have the formulas right here. So in this case, which formula are we going to use out of the 6 to differentiate this one?
The first one.
The first one, right? So, well, so that's number 1. So p prime of x equals number 1, 16, 1 over the square root of 1 minus the u quantity, which in this case is x over 4, quantity squared, times the derivative of x. What's the derivative of x over 4?
1 over 4.
1 over 4, 1, 4, right? All right, so, well, let's keep simplifying this. 16 over 4, that's going to give us a 4 in the numerator. And for the denominator, I'm going to do 1. I'm going to leave a space here. You'll see why. So that's going to square both numbers, x squared and 4, which is 16. All right, guys. So let me talk about this example, which, by the way, let me put a star right here. Whenever I put a star like this on exercises, that means that this is a very typical exam question. And I would like to stress on this one, because you will be asked to fully simplify this expression. And well, in this case, by fully simplifying an expression, we mean we don't want this complex fraction. You know, notice we have a fraction with fraction in between. So let's simplify this one. So, of course, there's a few ways. This is an over 1. And let's find an LCD inside of the radical, which in this case is 16. Multiply and divide by 16, that number 1. And let's put everything together into a single fraction. So that will be the square root of 16 minus x squared over 16, whole thing under 4. And for the denominator, for this complex fraction, we can use the quotient rule for radicals. That is, we can write the radical of a quotient as the quotient of 2 radicals. And of course, evaluate the one that we can evaluate, which in fact is the square root of 16. And the square root of 16 will be 4. Now be careful here. And here is where it might look a little bit weird, because which one are we dividing by which? Well, that's the lower the lower fraction. And what do we do in order to divide by a fraction, by the way?
Multiply by the
Multiply by the
opposite, the reciprocal.
by the reciprocal, right? So we multiply by the reciprocal, right? Which in this case is going to be 4 times the reciprocal of 4, which is 4 over the square root of 16 minus x squared. Which in this case is going to be 16 over the square root of 16 minus x squared. And this is a simplified expression for the derivative, all right? We don't want, I will looking for rational expressions inside of rational expressions, you know, and on top of that with radicals, all right? Questions about this example? All right, so how about we take a 10-minute break and then we take it from the next example when we come back. Let me pause on this.